Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Before we begin, a note from our sponsor. I'm Richard Jacobs, Executive Director of the nonprofit Finding Genius Foundation and host of the Finding Genius Podcast. In late 2016, I was rear-ended at 65 miles an hour by a truck on the highway, which sent me off-road into a ditch. The impact of the collision gave me a concussion and other injuries. At the hospital, a CT scan showed that I had thyroid nodules, which turned out to be cancer. It was then, when I had a biopsy of my neck, that I realized even if I was a millionaire, I wouldn't want a second or a third biopsy due to the pain and the invasiveness of it. And appointments at that time for thyroid experts were 3 to 6 months out. And I was worried about dying now, even if that was irrational. So because of this, I've decided to raise money to conduct a literature review on steroids, on the causes of anxiety and depression, a condition that affects well over 50 million people in the United States and hundreds of millions worldwide. Our goal is to create a codex, a guide that reveals all possible treatments for anxiety and depression for people that live with the condition, or for loved ones that have it, as my wife and my son do. To find out more about our fundraiser, visit findinggeniusfoundation.org and click on current initiatives. And now, to our guest.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. A quick note about the foundation. We've started on our anxiety and depression massive literature overview. We're going to be going through 5,000 plus sources and putting them all together into a comprehensive guide that showcases all the possible treatments for anxiety and depression. The main premise is that if you suffer or know someone that has suffered and they go to a practitioner, that person may know 2 to 3% of all possible treatments. What if we could assemble 20%? It would be a home run for people suffering. So to find out more, go to findinggeniusfoundation.org. And today, my guest is Diyar Talbayev, Ph.D. He's an associate professor at Tulane, part of the School of Science and Engineering. We're going to talk about spectroscopy, Femtosecond and Terahertz spectroscopy. So, Diyar, thank you for coming.
Yes, Richard, happy to be here.
Yeah, this area you work in is so fascinating. I love time lapse, and I'm sure everyone else does. But tell me about your research. What are you trying to look at with the high-speed spectroscopy you're doing?
Right, that's a good question. I guess the main thing I wanted to discuss is what we do with light. And I guess you already got into one of the main points that we use light that's very short in duration. And the fascinating thing about light is that once it touches something, either passes through or is reflected by a surface, it keeps the memory of that stuff, of that thing, or a material that it has interacted with. And then if we measure that light in some way, we can learn things about what's happening inside different materials. And then the femtosecond part of it comes in is it helps us to understand the processes that are fast inside the materials.
Oh, so what's the current, how fast can you observe light? How fast is the camera that you're using?
Right.
How fast is the pulse? Yeah.
Okay, it's a good question. So, right, the speed of these observations actually don't have to do with the cameras. Cameras are just as slow as our iPhones. But the speed of the observations have to do with how short the pulses are. That's our ruler, if you wish. And so the shortest available pulses, in the world, not necessarily here in my lab, but the shortest available pulses are now measured in attoseconds. So, femtosecond is, a fraction of a second that's very short. An attosecond is, dividing a femtosecond by another 1,000 times. So I guess technically, the world record would be sub-femtosecond. I don't remember exactly how many, but let's say tens or hundreds of attoseconds. That's the shortest that I know of. But again, in my lab at Tulane, we work with the shortest pulses that are maybe 20 to 30 femtoseconds long.
So in that speed regime, what are you able to observe? Like, have you tried to look at chemistry happening as it happens? Are you able to do it with that resolution, or are you just looking at light as it travels?
No, our main focus is, phenomena in materials. So chemistry would be an area of potential interest, but we work with solid state materials. What comes most to mind is semiconductor chips as a solid state material, or magnetic materials that are used in like data storage, that kind of things. And so the processes there have to do with what electrons are doing inside. In fact, if you thinking broadly, electrons determine the properties of everything we see around us, including the chemical processes. So my interest and goal is to see and observe what electrons are doing. For example, they could be making a material magnetic, and then we can observe the motion of tiny magnetic moments due to electrons inside materials. Or other common phenomena are electrons could be making something a good electricity conductor, or they can do the opposite, make some material a good insulator, electrically speaking. And then there are more exotic phenomena such as superconductivity, as an example.
But how fast do I know electrons are waves and particles, but how fast do they move? Is the speed at which you're able to observe them, quote unquote, fast enough, or what limitations do you run into? But what can you observe at the speeds you're using? Right.
So, one example that I gave is we can see how electrons' magnetic moments are moving. So that speed, let's say one revolution, for example, of a one precession cycle of an electronic magnetic moment, under some circumstances could be 1 picosecond long. So a picosecond is 1,000 femtoseconds. If we're using a femtosecond as our benchmark, then in 1,000 femtoseconds, an electronic magnetic moment can complete one of its revolutions. And, the light that we have allows us to observe that.
How do you probe the electrons? Are you using just a pulsed laser that pulses incredibly fast to do this, or how do you do this?
There are different ways. So, like one of our tools are these laser pulses, just like you said. They are visible to the eye, so they're red in color, and they last these 20 or 30 femtoseconds. And then what we do is we shine them. We actually shine a stream of these pulses on a surface of the material we are working with, and then we measure what changes in the stream of pulses each time they get reflected. Because these processes we're looking at, right, it's an evolution of some sort. And so by sending this stream of pulses, if you wish, we can look at like a stroboscopic movie. Each pulse is a time frame, and we can measure slight changes of how much light, for example, is reflected from one pulse to the next, and that can tell us something. Or we can measure other properties of this light. One property we can measure is polarization. And so we can measure slight changes in how polarized the pulses in this stream are from one pulse to the next. And that also changes something about what's happening inside. For example, often polarization is related to the motion of the magnetic moments of electrons. Like one of the basic properties of the magnetized matter is that it can rotate or change the polarization of light that's reflected off of a surface. So that's one example.
I know that the uncertainty principle bedevils all of physics. So where is that going to come into play if you try to go at a shorter time scale? Let's say you try to do an attosecond pulse laser. Will there be uncertainties that cause it just not to work? Will the energies be too high or too low? Like what do you work with in terms of trade-offs?
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
Right. So thinking in terms of just, if we're looking at just the pulses themselves, then I don't think we're we're running into that kind of limits. But when we think of them, these very short pulses interacting with electrons, then the uncertainty would be in how well, I guess, we can measure the behavior of the electrons, because there are different forms of the uncertainty principle, and in this case, the uncertainty principle would connect the pulse duration to the spread of the energy of either the light or the electrons that can be measured. So the shorter they are, the more uncertainty there is, I guess, in the energy of either of the electrons that we're interacting with, or the change in the energy during this interaction.
Okay, and you mentioned when light interacts with matter, it kind of affects the light in a permanent way. So what's an example of that? Like, what happens when light passes through certain materials? What changes about it?
Oh, the most obvious example, some colors can get absorbed. Like if you think about, colorful windows, for example, they're colorful, or if you're looking through a colorful window, the daylight that streams into is white, right? It has all the colors. And then as it passes through, we see all these colors because some of the wavelength got lost or got absorbed or perhaps scattered out of the beam or the stream of light that reaches our eyes. So that's the most basic interaction. Some of the wavelength can be absorbed or scattered. And in fact, this is exactly what we use when we study materials. Like I said, pretty much all of the behavior of the materials around us is due to how electrons behave inside. And electrons are also the main component, I guess, of stuff that interacts with light. So it kind of works out very well that way.
So what have you been able to tell about the structure or properties of various compounds by doing this spectroscopy? Okay.
Well, one of the main topics has been this example that I already mentioned. We look into magnetic properties. And when we look at magnetic properties, the magnetic properties are there because electrons have, in addition to electric charge, they have magnetic moments associated with them. And so when electrons manage to combine, they manage to combine in such a way that their magnetic moments add up together, that's when the materials can become magnetic. And these magnetic moments can also interact with light of appropriate frequencies. That's where the terahertz part comes in the name of my lab that you mentioned. So the light of these terahertz wavelengths turns out to be a very convenient and useful light to study the motions of these magnetic moments.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
By studying them, what we have learned a lot is about how the magnetic interactions happen in different materials. So that has been one of the main topics. Another, I think, a cool topic that we've looked at in recent years was, turns out there are materials that can pass light differently in the forward and backward directions. It's the names I use for this is either one-way window or one-way mirror, and it's not quite like the one-way window that you see in the movies, right, where somebody is behind a glass and they're looking into a brightly lit room and they see what's happening inside, but the person on the other side of the glass don't see. So that's not quite it. That happens, in the movie it happens just because one side is dark. You obviously cannot see into the dark side. If both sides of that window were lit equally brightly, then, you and your friends would be equally able to see each other. But then it turns out that there are windows that pass more light in one direction and less light in the opposite direction, even if both sides of it are equally bright. So that's one example of what we have studied recently with light. And then a counterpart to that is, turns out,
you said you deal with solid state materials. Is the spectroscopy of liquids or gases not workable at these speeds, or what's the issue? Is it just you can't do everything, or is it that liquids or gases are
right
completely different beasts?
Nothing. There are no issues. There are probably hundreds of scientists who do all those things. They study liquids and then they study gases. So
yeah, I just wanted to know, have you at least considered looking at the properties of liquids and gases or plasmas? And if so, would the speeds at which you do spectroscopy be workable for those substances, or do they need to be faster? What's the overall?
That's right. I think I repeat myself. There are probably tens or hundreds of scientists using femtosecond spectroscopy to study liquids, solutions, or gases. In fact, a lot of them are chemists. So chemistry, in my mind, associated with the squishy kind of things. In fact, I have a chemistry colleague who uses similar tools. I guess just my background as a physicist sort of rooted me more in a solid material, on the solid materials, materials side. That's all.
It'd be funny if someone sponsored an annual race of ultra high speed spectroscopy scientists, and they had to run this 5K race, and they were so slow, but the spectroscopy they do is so fast. I know it's silly. It's just something I thought of. So, okay. So you said there's hundreds of scientists working on this. Do you collaborate with them? Is anything they're doing useful to you, or is it kind of everyone's sticking to their own knitting, and it's only maybe through papers that you learn about high speed spectroscopy and what else it can do?
Right. So I have collaborated, and I am collaborating with some of them. Usually, there needs to be something common and then useful, for both collaborators that motivates. We all go to meetings, or used to go to meetings. We talk to each other. We read each other's papers. Like I said, I do have collaborators. For example, Louisiana State in Baton Rouge, Baylor University in Texas, Okinawa Institute of Science and Technology in Japan. So usually the motivation is that you can't have every tool in your toolbox. And so sometimes you just need to borrow a tool. And so you go to someone else's lab and do it, or you let other people come to your lab and use your tools. That's the most common motivation. But there are others, or, exchanging and sharing ideas is another great motivation.
What's the barrier to creating a 1 attosecond laser?
The barrier to creating 1 attosecond laser.
Yeah, like you said, the ones that you're using are hundreds of attoseconds. As in, you said, I guess the best in the world is the fastest, 20 to 50 attoseconds. I mean, what would be the barrier, physics-wise, to producing a 1 or sub 1 second, sub 1 attosecond laser?
So I think these shorter pulses, they don't come straight out of a laser. I think we usually, or the others usually, start with a laser that's fairly short, but not that short. So let's say a few femtoseconds, short, really strong pulses. And then they use usually a gas where they focus these long pulses. And as these long pulses get focused into a gas, they interact with the molecules or with the atoms. And these interactions are so strong that outcomes out of this gas, out of this interaction, come much shorter attosecond pulses. So it's, we have to do extra work. I don't think there are actual lasers that provide these attosecond pulses. We start with good old femtosecond pulses, and then we use these strong nonlinear interactions to convert these long pulses into much shorter pulses. And so in principle, if one looks at these interactions, actually, I don't do that myself, so I don't want to mislead here, but in principle, if you have, a strong enough input, then there may or may not be, imminent or immediate barriers to getting to shorter and shorter pulses. But again, I don't do that myself, so I'm not fully aware what's preventing us to make them shorter. But I'm sure there are practical difficulties.
Yeah, well, I'm sure there are. Yeah. Well, very good. Dion, what's the best way for people to find out more about your research? Where can they go?
I do have a website. So if one were to go to Tulane physics department, look up my name, there will be a link to my website.
All right, very good. Well, Dion, thank you for coming on the podcast. I appreciate it.
You're very welcome.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.